Yes, we can hear you. Okay, so you're our next speaker, Jordi Figueras y Ventura from Meteo Swiss. Can you start sharing your screen?
Yes, I will do that. Okay, can you see something?
Maybe a couple of seconds there.
Mm-hmm. Okay, please go ahead.
I can go ahead directly?
Yes.
Good. Okay, good morning or good evening or good night, I don't know, to everybody. Thanks to the organizers for inviting me here. What I'm going to talk today is about a couple of activities that have been ongoing at MetaSwiss related to lightning and convective cell severity. I have to acknowledge my co-authors, Alessandro Herring and Jacopo Grazioli. My talk has two parts. The first part is a bit more an operational application of our lightning detection network. And the second part, I'm going to summarize a study that we carried on 3 years ago already using lightning mapping arrays in the Alps. So let's go ahead for the sake of time. First, I'm going to talk about lightning jam as a storm severity predictor. So lightning jams, the definition is it's a sudden increase in total lightning, so cloud to ground plus inlet cloud flash rate within thunderstorm cells. And the interest of lightning jams is that they can occur from few minutes to several minutes before the onset of severe weather like hail, heavy rain, wind gust, etc. So how we do that at MetaSwiss operationally, on one side we have the radar network that Loris already talked about. On the other side we have the lightning data provided by Meteorage. And out of the radar network, we obtain these TRT cells, and out of the lightning network, we obtain the total lightning. And here you can see the evolution for one event of the total lightning. And you can already see that there are several jams, sudden jams in lightning activity. There was a first one here, and then a second one here, and here, and here. And this, on a systematic manner, what we do is, first off, we have the data every 2.5 minutes. So every 2.5 minutes, we have a TRT cell. So for example, at 15 minutes before the current time, there were a couple of lightning strokes detected. And that's where we would start the pre-alert of the lightning jam. And then what we do is we compute the standard deviation over the past 50 minutes. And if there is a jam, so that the total lightning is at least 2 times this standard deviation computed here, then we say that there's a lightning jam. And we issue a warning that the forecasters that it's seen by the forecaster. Operationally, it looks like that. Here, what we see is the first of the total, the probability of hail, maximum probability of hail over 1 day. And overimposed is these triangles here are the lightning jam warnings. And in general, what you can see is that these lightning jams correlate quite nicely with areas where we had high probability of hail. So it can be used as a complementary nowcasting tool for severe weather. We did some statistics about how useful this can be. Over the time with a single lightning jam or multiple lightning jams. And we can see that for ordinary storms, there were not that many lightning jams, but for storms where the probability of hail was relatively high, the frequency of lightning jams was relatively high. So it's a bit modest, but there is some skill in the detection. There's a probability of detection of 45% and a false alarm rate of 29%. And it has a lead time on average of 18 minutes, which is quite an interesting thing to have. So that was for the lightning jam. And the second part of the talk, it's going to be a bit more experimental. Here I'm going to talk about a measurement campaign that we carried on in the summer of 2017 with colleagues from EPFL and from the University, Technical University of Catalonia and Meteorological Service of Catalonia. And what we did there, well, there were several questions we wanted to address. One is, can polarimetrical variables inform us of the likelihood of lightning activity? The second would be, can we distinguish between precipitating conditions producing mostly intra-cloud lightning from those producing cloud to ground? And what are the environmental conditions leading to upward lightning? This is a question that I'm not completely at least here. There's another paper on that. So what we did there was our colleagues from the Technical University of Catalonia provided us with this lightning mapping array consisting of 6 sensors. It was a very basic network, and we installed them around the Santis Tower, which is here. Here we can see the location of our radars, Alvis and Weissflug. Let's zoom in. So here is the region where we installed these sensors. Santis Tower is here. We were interested in this area because the area of the Santis is known to be a hotspot for lightning. And the campaign took place over the summer. And what we did was we tried to collocate radar measurements with lightning detection from the LMA. Here you can see an example of the trajectory of the lightning respect to the radar in radar coordinates. And here you can see for one lightning, this is a copy at 5 kilometers and with VHF sources detected by the sensors overimposed here. I hope you can see it. It's a bit small. So with that, we can have a statistics of where the lightning was originated and where it was propagating. That's what we were interested in. Here you can see again, as a function of time for a single flash the different polarimetric parameters and the results of our illuminator classification. This is the sort of data we are going to deal with. So there was another point that we had to associate a flash detected by the lightning mapping array with an Euclid slug, so a slug on the ground, because the lightning mapping array simply, due to visibility issues, it doesn't not see on the lower part of the atmosphere. And for that, we used a time criteria that was 0.1 seconds from the first and last lightning mapping array source, and an area criteria that was 1.2 times the minimum rectangle covering the extension of the LMA flash with a minimum of 25 square kilometers, because sometimes we had lightning that was really moving very sharply down. So we focus on events where we had lightning 2 kilometers from the tower, and because this was a campaign where the instrumentation was unmanned, not all the sensors were working all the time. Finally, we came up with 8 days where the quality was quite good. That corresponds to 1.5 million VHF sources and approximately 12,000 flashes. 10% of them were cloud to ground, according to our classification. You can already see that there's a clear diurnal cycle, I would say. Most of the lightning was produced late in the afternoon. And here you can see where the flash sources were located. Here there was a clear blockage from the Alps, so there was better view north of the Alps. So let's have a look at some statistics here. These are the value at flash location, and for flash origin we mean the first VHF source that was detected from a flash. You can see that most of the flashes were located at quite high altitude. They had the origin around 8,000 meters. It's hard to see here, but for the cloud to ground flashes, the location was slightly lower at of the location of the origin was slightly lower, and you can also see that they were located in areas of fairly high reflectivity, considering that it was well above the ISO 0. On the other hand, they were propagating. Yes, some of them were staying more or less where they were generated, so around 8,000 meters, but most of them were propagating to a lower altitude, around 4,000 meters. This is where most of the VHF sources were located. And same here, although most of the flashes were propagating in areas with very high reflectivity, there were quite some that were propagating in areas of modest reflectivity. But probably what is more interesting is looking at the microphysics of the thing, and here is what I'm showing. On the top there is the the values at flash origin, and on the bottom is where they propagate. And you can clearly see that a huge percentage was generated in areas where there were either ice, hail, or rime particles, a little bit less on aggregates. But at the same time, the entropy was quite high, meaning that there was a mix of species. Most of the flashes originated in areas where there are at least two different species, more or less in the same area. And they also propagated, in general, they propagated also in areas of rime particles and ice hail. And again, there was quite high entropy, and there was quite a number of different species. Rime particle was dominant, but there were other species there. There's one thing that we found is that upward lining has slightly different characteristics. Here we can see the location of this upward lining. And by upward lining, we define it as lining that first appeared in areas where there was liquid or mixed phase. And already you can see that there are a couple of clusters. One is clearly the Santis Tower, and then there's another one south of it. And what is interesting is, well, here is simply to show that indeed they originated much lower in the atmosphere. But what is interesting is that they propagated in areas where not necessarily where we had a very, very strong reflectivity. And here you can also see that there were almost two modes of propagation. Most of them stayed relatively low, so propagating horizontally almost, and so but some of them went up quite high, actually. Here there are the values at flash origins. By definition, they originated in areas of rain or wet snow. Although the entropy was very, very high in these areas. What is interesting is that there are two things that are interesting. One is that there was not that many that propagated in areas of ice hail. Most of them were either rime particle or aggregates, which suggests that you don't need to have very severe cells to have this upward propagating lining. And again, the entropy was quite high, and there were several species in the same area. So one complementary thing about that is what we call, knowing that that lining propagates mostly in areas of rime particles of hail, we created this indicator that is the rime particle column height. That is the height of the column inside the convective cell that we define via the TRT algorithm, where rime particles or hail are dominant. And what can be seen here is that there's a clear relationship between the height of this rime particle column and the amount of lining detected. So that potentially can be used as a descriptor to indicate the likelihood of lining. So I already come to my conclusions. First is that we have seen in the first half that the sudden increase in total lining in a convective cell is a relatively good predictor of increased cell severity. And from our little study, we showed that most flashes are originated in areas of high reflectivity, well above the ISO 0, and containing rain particles and hail. And they propagate predominantly through areas of rain particles or hail. But upward lining has distinct characteristics, and that's important because the height of the rain particles can be a good indicator for lining activity, but you also have to, okay, it doesn't matter. You also have to consider the orography and probably the past situations to have a better predictability of lining. It's not enough only to focus on the presence of rain particles. And with that, maybe I will try to get back to the presentation. Okay, here it is. I thank you all. And if you want to read more about the study we did in the Sentis area, there are these 2 papers that were published, among others. Thank you very much. I'm ready for questions if there's time.
Okay, thank you very much for the nice presentation. Yes, we have a question on Slido from Silke Tröme, and she's not in the speaker room. So I think I will read out the question. Thanks, Jordi, for the nice presentation. Are you also planning to investigate the information content of the polarity? I read some time ago a paper from the 80s, but not aware whether something goes on at the moment in that direction.
Polarity of the lining strokes, you mean? I assume.
Yeah.
Yeah, we did this study. We found out statistically it was very difficult to see whether there was any relationship with the lining activity, if it was positive, negative, etc. You needed to have some context to study really the profile of the individual cell. Out of the statistics, what we clearly saw as a clear signal is that you need rain particles and hail for the production of considerable amounts of lining. But whether it had positive or negative polarity, then you had to really enter into the study of the individual cell and the structure of the individual cell. I hope that answers the question somehow.
Okay, thank you very much.